Hi, hello, I'm Kiran Kumar from Nature of Physics and Art. Welcome to my channel. Today topic is electric field intensity and electric potential of a line of charge, that is uniformly positive charged wire, with the help of Gauss law. Okay, step by step I will do the videos based on the Gauss law and electric flux, and please do subscribe and like my channel and share to your friends also. See now, first based on the Gauss law I will do this. See, what is Gauss law? The total electric flux through any closed surface is equal to 1 by epsilon naught times the net charge. What is electric flux? The total number of electric lines of force passing through the surface and normal to the surface is called electric flux. So from the Gauss law, that is phi, which is equal to closed integral E bar dot ds bar, which is equal to q by epsilon naught. See, this is the linear substance. For this, uniformly positive charge is there, and electric field intensity we can find with the help of assuming Gaussian cylinder. And here r is the radius of the cylinder, small r, and L is the length of the cylinder. So this is the L, which is length of this cylinder. Okay, and this cylinder has total 3 surfaces, in which 2 plane surfaces and 1 curved surface. So for example, chalk piece, 3 surfaces it has, in which 2 plane surfaces, top and bottom, and next 1 curved surface. See, for this electric flux we have to find with the help of 3 surfaces. Okay, so and before going to that, we have to find the linear charge density. So that linear charge density, so this is indicated letter lambda. So lambda is equal to q divided by L. So for this, charge q, which is equal to lambda into L, is taken as equation number 1. Now with the help of Gauss law we can find the electric flux. So electric flux due to 2 plane surfaces, Okay, so first try to understand. I am taking S is the surface area and ds is the small element area and ds bar is the area of vector. Okay, so for this is taken as surface area ds, and this is the area of vector. So ds bar is the area of vector, and here electric field is radially outward direction from the positive charge. What is the angle here? 90 degrees. So theta is 90 degrees. Okay, and this is taken as flux is phi 1. So this is taking flux is phi 1. Okay, and this is the another plane surface area. So here ds bar is the area vector. Okay, so ds bar is making an angle 90 degrees with the electric field. Electric field is from the positive charge. So this is the E bar. So here also theta is equal to 90 degrees. So 90 degrees. See. Okay, this flux is taken as phi 2. And 1 curved surface is there. This area is ds and area of vector is ds bar, and electric field is radially outward direction. So this is E bar. In this situation both are same direction, theta is equal to 0. Okay, because of E bar and ds bar is along the same direction, and this area flux is taking as phi 3. So this is the flux is phi 3. Try to understand step by step we will do. That is electric flux due to the 2 plane surfaces, that is phi 1 and phi 2. See, in these two conditions, in these two situations, here electric field vector and ds bar mutually perpendicular to each other. So we can write electric flux phi 1 which is equal to phi 2. See, perpendicular only, directly writing phi 1 is equal to phi 2 is equal to closed integral E ds, okay, cos 90 degrees. So here theta is equal to 90 degrees. So here phi 1 which is equal to phi 2 is equal to 0 because of cos 90 is equal to 0. 0 into anything is 0. We got two flux due to the plane surface is 0 with the help of Gaussian cylinder. And next one is curved surface, that is electric flux, okay, due to one curved surface, that is phi 3 which is equal to closed integral E bar dot ds bar, that is eds cos 0. Here theta is equal to 0 for this, okay, and cos 0 is equal to 1. We will get phi 3 which is equal to closed integral E into ds. So we got here three flux due to the, okay, uniformly positive charged wire, that is line of charge. Okay, next, based on the total flux, that is phi is equal to phi 1 plus phi 2 plus phi 3. Phi 1, phi 2 due to the plane surfaces and phi 3 is curved surface. Then we will get the electric field intensity. Just a second, I will clean the board. Okay. See, now we got phi 1 which is equal to phi 2 which is equal to 0 and phi 3 which is equal to closed integral E into ds. So now total flux. So total flux phi which is equal to phi 1 plus phi 2 plus phi 3. Okay, for this phi which is equal to 0 plus closed integral E into ds. Okay, according to the Gauss law. Okay, so that according to Gauss law, so here closed integral E bar dot ds bar, okay, which is equal to q divided by epsilon naught. So from this equation phi which is equal to, we got here, okay, closed integral E into ds. So we can write, so E into ds which is equal to q divided by epsilon naught. Okay, so here closed integral E is common, closed integral ds which is equal to, here q value is replacing from this equation, that is lambda into L divided by epsilon naught. Okay, integral ds which is equal to 2 pi RL. Why? See, this is the circumference is 2 pi r and height is L. So total surface area we will get 2 pi r into L. 2 pi r is the circumference and height is L. So 2 pi r into L. So we will get here E into 2 pi r into L which is equal to lambda L divided by epsilon naught. So we got integral ds which is equal to S which is equal to 2 pi r into L. 2 pi r into L. Try to understand this. Okay, just a second, I will clean. See, now here already we got this equation. Here LL is get cancelled both sides, so E is common. So that electric field intensity I'm going to find. That's why E which is equal to lambda divided by, this is 2 pi, okay, r into epsilon naught. So we can write here E bar, which is equal to lambda divided by 2 pi epsilon naught into r into n cap. So where n cap is a unit vector. Oh, or we can write here like this also, epsilon naught into r. Okay, anyhow result is same only. This is the electric field intensity of a uniformly positive charged wire or line charge, and based on this I will find this is taken as equation number 2. So based on this equation from the EVD relation I will find the electric potential continuously. Okay, because of the EVD relation video I did, just watch that video, then you can easily understand. Okay, just a second. Now we will discuss electric potential of the uniformly charged line, that is line charge, or another name is electric potential on the straight charged wire, infinite. See, think practically here. We will discuss based on the electric field intensity and EVD relation. So that here E, which is equal to minus dV divided by dr. E is the electric field intensity, V is the potential, and R is the radius. EVD relation. Okay, so for this I can write dV, which is equal to, okay, minus E into dr. So V, which is equal to minus integral E into dr. Okay, integration, that's why integral dV is equal to V. So this value is replacing here. So electric potential V, which is equal to minus integral E value is lambda divided by 2 pi epsilon naught here dr divided by r. Okay, so here V, which is equal to minus lambda divided by 2 pi epsilon naught is constant, integral dr is, we can write one more step, integral dr divided by r. So for this, minus lambda divided by 2 pi epsilon naught log base A r. Integral dx by x is log x. Integral dx by x is log x. Integral dy by y is log y. Integral dr by r is log r base E. So here we got electric potential, that is minus lambda divided by 2 pi epsilon naught log base E r, okay, plus C. C is the integration constant. This is the formula we got electric potential of a uniformly positive charged wire or line of charge. So try to understand whatever we did first. Based on that electric field, we are finding electric potential. So step by step, this is sequence, that's why I'm doing at a time. Electric field intensity based on the EVD relation, electric potential. Thank you. I will continue with another video, that is electric field and electric potential of a plane sheet.